Swayam Prabha. Digital India. Educated India.
I am Saheli Bhadra. I'm assistant professor in IIT Palakkad, and I research in machine learning, multi-view learning, kernel learning. These are my topic of interest. So, what do you know about machine learning? What you have learned here? Some terms. Clustering and linear regression, optimization. This is the definition of you are telling this is machine learning. Okay. So you know regression? Okay. So what is regression?
Model the function can give us an output, a numeric output from a set of features.
Okay. So in regression is a supervised learning. So do you know the term supervised learning? So here we will have some training data set with the training labels. So we have that supervision of training labels so that we learn a function which map from feature space to the output value, and with the help of giving output value or the training data we learn this function, and then after learning we predict for the unknown data. And how do we want to predict it is that in the unknown data our model should perform well. So this is called the generalization of the model. Did you have heard about this term generalization? Bias variance, regularization. Okay, good. Now today we will learn about classification. So what is the classification? This is one type of supervised learning. But I prefer to say that it is more easier for the model to learn a classifier than to learn a regressor. So we learn linear model for classification. I think you know the linear regression. So we'll see what is the linear model for classification. And as an example, we'll learn logistic regression. And if time permits, then maybe linear discrimination analysis. So these are the things we'll learn. What is classification, how it is different from the regression, what is Bayes' rule for classification. Do you know what is the Bayes theorem? Good, very good. Okay, let's see. So these are the example of classifications. So if one patient comes to an emergency room with a fever and some other headache, body ache, and now this is a very crucial classifier whether he has a Nipah affected or not. So this is another example is some mails coming to your box, whether this is an important mail or it is a spam mail. Even it can be like which sequence of DNA is associated with phenotypes. And even you can think about prediction tomorrow's weather when it is categorized, like whether it is sunny, whether it is raining, or it will be cloudy. So can you then guess what is the difference or what is the specialty in this classification? We are actually telling the output is category. It's either Nipah or not. So it's a two label classifier. It is either sunny, rainy, or cloudy. So it is three category we are going to classify it. So it is discrete. So that's why they are all classification problem. In regression, we could have the linear, some continuous output, real valued. But here mainly we'll have some discrete output. So this is the picture of famous Irish data set which has been introduced by Fisher. And this has been used for many papers to demonstrate how their classifiers are working. So this is the three type of iris flower: iris versicolor, iris setosa, virginica. So what is given in the data set is that these three types, what is the types or the category of the flower, as an output or Y, and as a X it is given what is the petal length and what is petal width, and also what is sepal length and sepal width. So as a data set for the classification task, we'll have again a paired data xi, yi, where xi is a vector. For iris data, we have a 4-dimensional vector: sepal length, sepal width, petal length, petal width. These are our 4 features for every samples. And there is one class, it's maybe 0, 1, 2. So we can write the class as we like to. So it can be 0, 1, 2, 1, 2, 3, even you can say ABC. So for generally when we do binary classification task, that means we'll have 2 classes. There we denotes either as a 0, 1 or as a -1, 1. So as per the model's requirements. So now to have a flavor of what is classification, now just think about only one feature, which is here in the x-axis. So you can see in this x-axis, it has the petal length. And y-axis is saying that whether it is a setosa or it is a versicolor category, subcategory. So here it is saying that if petal length is below 2, then it is setosa. And we denote the setosa as a 0. And also it is showing it is if the petal length is more than 3, then it is versicolor. So and we are denoting versicolor as a level 1. So now we have to learn a function, what I said in words, that G as a function which will map from X a feature to a Y, so that it will be given the correct classification. How we can say, oh I'm sorry about this error, it should say like Gx equal to 1 if xi is greater than 2.5. Okay. So we'll have some classifier here. So here at the 2.5, so that if it is below 2.5, then it is a 1 class, it is above 2.5, then it is other class. But we want one thing you have to keep in mind, that not in the training data we want that classifier to perform well, but also to perform on the test data. So now how do we measure the quality of the fitting in the regression? How did you do that? How good is your regression? How did you calculate? How did you measure that? Squared error between the actual value and the predicted value. So can it helpful for the classifier? It's not needed, that error. So here error is only whether it is correctly classified or it is misclassified. So if we have like k classes, then we'll get such a matrix. Like for this will be the true classes, this side, and this side it will be the predicted classes. The columns are the predicted classes and rows are the true classes. And if there is some misclassification like this point where the true class is C1 and it has been predicted as a C2, then we will have some loss. And a total loss for the classifier will be the sum of all these elements in the matrix. Okay. Now we want to minimize the loss even in the test data. So there we'll have, I would like to introduce some term is called risk. It is like expected expectation of the probability of error. So if you think that one data point is coming from a probability distribution, and then you will take the average error for all probability distribution, you have to minimize. So you can say that we have to minimize over all x and y of loss given by this classifier G, and that if we take the y as empirical error and then it will be will be taking only the expectation over x, and the y goes inside this term, and so this will be our error. So it is like that if the true class is ck, but classifier has classified is a y hat, and then the probability of the data point to be in ck. So did you learn about this generalization error for or the regression, these things, or this is very new to you? Very new? Okay. So did you get this thing? So what will be the loss here? The loss is actually it is the y, actual class is y, and the G has given the label as y hat. And now we have to get expectation over all y and all x. So x may be in a continuous distribution, but y we know that it is a discrete and we have only k classes. So for taking expectation of the k classes, we just sum it up. Just how we take mean, empirical means, sum and divided by the total number. So you can here we can omit this by k, but this is the loss when y is k, small k. So and this term is given this, that what is the probability of x to have true class ck. So this is the probability of pck, and this is the loss for the true class ck. And then we want to, when we will be learning classifier, then we want to minimize this risk. So that will be taken such y as a y hat, so that this sum will be minimized for all the x individually, independently. So we will assume that all the samples are independent to each other. So we will take the point wise minimization over all the xi's, and then we can get a minimum, we can learn this function for a x. So this is also, this classifier which minimize this risk is called the base classifier, and this is also the error, the risk of the base classifier is called base limit. This is the minimum possible error or risk we can get for a classifier for this data set. We cannot do the better than the base classifier, or we cannot get the better limit than the base limit. So maybe it will be easier if we go to the binary case, not the multi-class cases. So let's see that, okay, before that, what can be our this loss? This LG function, what we say, this is going to be the loss for misclassification. So for very simple loss function, we can take this is a 0, 1 loss. So 0 loss when it is correctly classified, and it is 1 loss when it is misclassified. And then so this we have a x, this is our and we have a y. So y is in 0 and 1, and this is the probability distribution of So if you think about, if you remember that we have said that if the probability of y is y equal to 1 is more, and then the probability y equal to 0, then we should give it as a class 1. So here you can say up to this point we'll be having this probability is more, posterior probability is more, and so if the x is here in this point, then we'll say that here the g of x is equal to 1. And for this region, we'll say that for this side, g of x is equal to 0. So this is the base classifier. And what is the amount of risk the base classifier have is this much. So actually these two bell-shaped curves should cross in the same point where the line is. So that this side, this will be the error part. Here this is the error part, and for this one, this is the error part. So that for this thing, the base classifier has said that the class is 1, but actually the 2 class was 0. And therefore, the loss is sum over this. For this, the loss is this is a true 0 and it is 1 predicted, and then the loss is, this is the, what is the probability here, that it's equal to 0 and given x and 1. So here the loss is 1. I can get it, sorry, and the 1 for this part. This is the probability here. And then for other part, we'll be having this part. We have the gx has said this is 0, but actual the 2 probability was 1, and so we'll have another loss, that probability of y equal to 1 given x by 1 into 1 again. Okay, so this is the base error, this is the minimum error we can get. I did not get it, is whether it is clear. It's not. So which part was not clear? Yes. I did not get. Okay, so what is the intuition behind this diagram? Good. So do you remember this thing? We have here few points where it was a sepal length. So this was sepal length, and we have some other point here. So here it was 0 and 1, right? Now if you say the probability, so with this sepal length, what is the probability here of y equal to 1? So this is the has a high probability here in this part, y equal to 1, y equal to 0. It has a probability, high probability here. So maybe I should draw some other thing. So here it is again. So I'll put this color. So there are two curves. One is this will show this probability of y equal to 0, and this curve will show you the probability of y equal to 1 for a given x. So for this, if we have x here, then what will be the probability of y equal to 0, and what is the probability of y equal to 1 when our x is here? So probability of getting 0 is 1. So here, and it is getting 1 will be here. So like that if you draw, so here also we will get like this, and for other things it will be like this. And then at some point we are changing it to here. So it's become here. So when your data point is somewhere here, like at 4, then it will have the probability of y equal to 1 is higher and probability of y equal to 0 is lower. So in that case it will become here, this plot, right? And as it is a probability plot, means we are just giving a smoothness of this curve. Okay? And then this is the smoothness of this curve. So we can say that if we draw a separator here, then this side, this will be the y equal to 1 will be the higher. Probability of y equal to 1 given x will be higher. And with this side, the probability of y equal to 0 to be x equal to higher. Okay? Now this side, there is some part where there are some samples which has the true class 0, but we are classifying it as a 1. So that's why this small probability part will create a problem, will give a error. And also for similarly for this part, it will have true class what? What is the true class for this part? 1. And what is we have, our G classifier has classified it? 0. So this part will have, we have then loss. What kind of loss it is? True class 1, and then we have classified it as a 0. And what kind of loss this part is? L0 1, right? Now how do you know what is the total amount of the loss? Loss into the probability of this part. We need to find out the whole area of this part. So then this total area, this loss is going to be, the total area is loss 1 0 in probability, this probability. So probability of y equal to, so it is this part only. So how we can say the probability of y equal to 1 and g of x equal to 0. So it is the part where we have the actual label 1, but we have classified it as a 0. So this is this probability. Okay, and then we can have this part. So now whether we can learn a classifier with a regressor. So it is okay, we have the categorical classes 0 and 1, right? Can we learn a regressor? Yes? Who said it's yes?
Only if the output range is between 0 and 1, like if the output, possible output is between 0 and 1, we can
Do you have any such restriction for learning a regression? So what you are saying, that if we can one regression that will give only output 0 and 1, then only we can learn it?
And if there is such a data set whose output is always lying between 0 and 1, then to predict that regression value is
Okay, if you have such a regression that has a 0 and 1 output, then how will you use it as for the classification?
the value is closer to 1, like round up.
Round off. That means you will saying that whether this regression value is greater than 0.5 will be put at 1, and if it is a less than 0.5 it can. Then what happen if your regressor is giving output as 2? You will bring it to 1. It will be closer to 1. Is that possible? Yes? Yes? So we can learn a classification with the regression. Anybody has any objections about it? No. I have. Why? I'll show you. Okay. So, so the thing is that this is this such points we have put. The same example. That we have few points here and we are learning this blue curve is a regression. Right? And then we can get a cutoff here at the 0.5. So that whatever the below 0.5 will be the class 0 and who are the above 0.5 will be the class 1. So this is coming from the same distribution, few samples I have taken. So it is perfectly working, some learning some linear regression and then put some quantizer above it. But if we go to the next example, let's our samples are little different. So if the samples are like this, if you think about the right hand side picture, then we learn again these blue linear regressions, and now if we cut it off at 0.5, then we are doing some misclassification, we are losing some error point here, because it is little, there are more example in that side, that's why it is not having the perfect slope of in the perfect point that will get if we put the quantizer at 0.5 will be not performing well. So we can see if we change our threshold or to like maybe 0.4 or 0.3, then we are working well. So in that case, you have to, after learning the regression, you have to change the threshold. It is depending on your data, depending on your training sample. That is not acceptable in machine learning or in classification. We cannot change our hypothesis like this. And one more thing is that, so if you think about the regression, if you think about the L2 loss, so something is given the output as 2, where the actual class level is 1. Should we have any loss for that? Yes or no? Should we have for the classification or regression? So think about, this is a regression problem. And our actual output is 1 and the G, or maybe I should use F. F of x is 2. What will be the loss for regression? For regression, what will be the loss? Square loss, somebody says no? So it will be 2 minus 1 whole square, right? And if it is a classification, so the y is equal to 1 and our fx is given two. So what should be the classification loss? So this is a positive class, and if you at all put your threshold at 0.5, then you will be correctly classifying it, right? If your gx is equal to 1, if f of x is greater than 0.5, so then you are correctly classifying. So your classification loss should be here 0. So it is not good to reduce the L2 loss for the classification. That's why we have introduced the loss 0, 1. So that is why with the linear regression, we will not be able to learn a better classifier. So somebody has asked this question, why I don't want to learn regress classification with the regression? Did you get my answer? Did you get it or not? Please answer, otherwise I will not be able to. It is clear now why we should not go for the regression, linear regression for learning classifier? Clear? Okay. So, but as I don't know his name. Somebody said like if we can confine our output for the regression in between 0 and 1, then maybe it will be used as a classifier. So, can we do that?